Okay, in this video, I will briefly introduce the motivation to do such a design and then talk about 3 different ways to reach the goal. After that, I will briefly introduce UMLE, on which I build my implementation and do advanced design. Next, I will illustrate my own implementation in detail. And at last, I will show my evaluation of the implementation and conclusion. Here we start. The cloud storage services grows more and more popular today. Most of us know Google Drive or Dropbox, but conflict rise when clients want to protect their data privacy, while cloud service provider would like to do deduplication to save storage space. If we encrypt messages by regular schema with different keys, the ciphertext will be totally different, even if the plaintexts are all the same. And deduplication cannot be done. In such situations, a basic idea is convergent encryption. It derives key from plain data and encrypts the data with that key. Thus, as long as the plaintexts are the same, then the key will be the same, and as a result, the ciphertext will be the same. And we compare the tag to detect duplication. But such a configuration has a vital flaw. That is, even if there is only 1 bit difference between 2 plaintexts, then the ciphertext will be totally different and disallow deduplication. And 2 advanced schemas can solve this problem: block-level MLE and updatable MLE. They have 2 core advantages. The first one is, as I said before, they allow block-level deduplication, so difference in one block will not affect deduplication of others. Another advantage is that they allow parallel computing while regular one does not, because when computing digests and encrypting the message by convergent encryption, the computation of latter part will have to wait the output from the former part. But if we encrypt on block level, we don't care about other blocks output. Then I will talk about updatable MLE. I use it as basic feature to build my implementation. Here, I will briefly illustrate some security factors. Strong tag consistency. It is used to measure the strength to resist duplicate faking the tag. Such a tag will make an honestly uploaded file wrongly discarded. Privacy under chosen distribution attack on block-level encryption. It is a privacy factor to measure how strong a schema can protect privacy. Context hiding. It is a self-defined factor in updatable MLE. Since UMLE allows update, this factor measures the ability to hide modification behavior. Proof of ownership security. POW is used in client-side deduplication. If one provides only a file tag and claims that he has the file, he will be asked to provide the tag of part of the file. If he failed to do so, then he will be asked to upload the whole file. And such factor measure the security of POW process. Since my implementation is basically based on the schema, I will simply borrow the conclusion and claim that it reaches the security factors above. Here is the main structure of UMLE. Let me briefly introduce BLMLE first. BLMLE allows users to keep only a master key to decrypt all the blocks. That is because all the block keys are combined together to compute a digest as master key, and encrypted with that digest. Then the keychain is also uploaded to the server. For UMLE, we can see that it is a little different from BLMLE. It combines some block keys to form a new block and derive the keys again. At last, it forms a tree structure of keys, and the master key lies on the top. UMLE also have 2 core advantages compared to BLMLE. One is that when there is difference in one block, such a design will only influence a root-to-leaf path and still enable block-level deduplication and multi-threading, while BLMLE influence the whole key chain and perform like a regular convergent encryption. Another advantage is that this schema introduced a new digest library called incremental hash. This library allows recomputation of the file tag when part of the blocks updated. It will first perform division by the old block digest and multiplied by the updated one to form a new file tag. An update operation also requires recompute only on the root-to-leaf path. Here comes my own implementation and design. I will first, the language used is CPP, and I will first illustrate the key parameters of my implementation and the external library, and then I will illustrate some additional design of my implementation compared to the regular MLE. And here comes the key parameters: block size. I allow self-defined block size, but in practice it should be fixed. And the key size is fixed because it should fit the key size demand for AES 256. And proportion is important to form the whole structure of the keychain tree, and I will illustrate it later. And number of threads, because I allow multi-thread, so I allow self-defined number of threads to test the performance of under different threads. And block num and last in claims, that is because I allow flexible file size in my design, so I should add some more parameters to rebuild the original information of the encrypted file. Here are some external libraries: SHA-256 to compute the digest of blocks and compute the keys, and AES-256 to perform an encryption of the blocks, and PBC is an incremental hash library to compute the tag of the file. Here are my additional features. One is that I enable flexible file size. I make this attempt to make the schema more approach to practice use. Another is multi-threading. I implemented multi-threading to accelerate the encryption process. I measure the performance and give the result in the later part. When talking about flexible file size, let's review the UMLE structure first. We can see that the proportion of block size and key size is 2. That means 2 keys can form a new group. And we can see that it only allows block number to be the power of that proportion. And besides, all the blocks should be the full size blocks. To enable arbitrary file size, my idea is to do bit padding. Here we can see that based on the original block number, we can compute the padding strategy. I compute it and stop the pad number of each level in a stack. When encryption, I read the number at the top and do bit padding and pop it and go to the next loop. I repeat it until the stack is empty, and at last I get the master key. And one should be mentioned is that I construct the tree on key level rather than block level. That is because I do bit padding, and padding on key level will dramatically reduce the padded size. I've also implemented multi-threading. I've used the 2 ways in my implementation. The first one is dividing the whole file into number of threads blocks and assigning one part to one of the threads. I used it in encryption process. Another method is reading number of thread blocks for each time and assign one of them to one of the threads. I use it in key generation process. That is because in some block number, the previous method may cause some wrong division. For example, for some block number, I divide the bottom keychain here, then the 2 threads have to wait for each other before computing the key 7. And if we cut based on the full block size, say here, of course, it will not happen for this block num, but for others, it may happen and make all the threads wait for the slowest one. So even if it is dealt properly, the computation time will grow if I use the previous method. At last, I evaluated my implementation on 2 dimensions: space cost and time consumption. For space cost, I measure the data size, metadata size compared to the whole file size. I fixed the block number to be 1024 and write the code in Python and draw the diagram. We can hardly see the blue curve. That is because it almost interferes with the red one under such precision. It means that the proportion of metadata size and the whole file under the 2 schema is very similar. And we can also find that the block size grows when the block size grows larger than 4K bytes, the metadata size is trivial. And for time cost, I run the testing program on IE computing cluster and get the result. The total data size and block size are given here and here. The cluster has 8 cores, so I run maximum 8 threads. And we can see that the speed doesn't grow linear. And we can also see that sometimes more thread number will even result in a slower speed. For example, 4 threads is slower than the 3 thread. But for different machines, the situation is different. I also run it for some run on my ARM Mac and IE Linux machine, and their 4 thread speed is faster than 3 threads. So here we can conclude that we had better define our block size to be more than 4K bytes to make the metadata size ignorable. Also, we can see that multi-thread dramatically improved the speed, but for different machines, the optimal thread num has to be tested independently.